Okay, so thanks, Joan, for the introduction. Also, thanks for inviting me. I'm very honored to be part of this celebration. So, as many of us in this room, I took Stefan's class at MVA, but I also took Yves Meyer's class and I failed it. Okay, so I never told him, but maybe I should. but anyhow, so I took Stefan's class, and of course I had to. I read the book. The wavelet book at the time, I think first edition, which I bought at Gibert at the time, and I'm still like looking at it every quite often. Okay, not every night. Okay, I'm not. I cannot tell. Okay, I say I wouldn't tell. Okay, and also now, like decades later, okay, as a member of the machine learning community, I'm very happy that Stefan joined our forces with the two mindsets that Dave was describing, and this amazing creativity. So we were happy that you try to come and work with us. So today I'm going to talk about not like recent work, but mostly trying to look back at past decades in machine learning and to see what were some of the reasons for achievements, and also what are the open problems. And I think I've named this a quest for adaptivity. And hopefully you see what I mean throughout the talk. So this is a classical like formalization of supervised machine learning of some data x, y. X can be an image, y can be a label on the image, and you observe some xi, yi, and the goal is, given a new x, predict a new y. Okay, so you assume you have access to some data. Okay, so very, very classical. And there is some loss function. Okay, so if you do classification, you can do the 0-1 loss, you can do logistic regression, least squares, whatever you want. It's not doesn't really matter. And the goal is to find from that training data the function f that is minimizing this expected risk, as you see here. And so this is a classical machine learning problem, and we know the solution. Okay, so if you know the distribution, you should predict with the z that is minimizing the posterior loss. Okay, so this is we have seen one instance in Eros Simoncelli's talk this morning. And if you do regression, you just compute conditional expectations. Okay, so it's just a summary of what you need to know for the talk. And now the goal is, how do you build such estimators? Okay, so of course you don't know the probability of y given x, so you need to estimate it from data. And how do you do it? So there are two main principles that have been like around. There are probably more, but that can see them as variations on those two. Either you do local averaging or you do empirical risk minimization. So what I mean by local averaging is that since I have a formula to get the optimal predictor, I just minimize the posterior loss. If I can estimate the posterior distribution for any given x, if I can estimate pure y given x, I just apply the formula. And if I do regression, I just compute a conditional expectation. Okay, so this is just machine learning is very simple. Just estimate distributions. So this has many instantiations. So you have k-nearest neighbor, you have kernel regression, and essentially those are often called local averaging because you end up like for any x, okay, you look around you and you average the labels which are around you. So either by counting the k closest to you or the k within a certain radius or any form of locality. Then there's another principle, which is maybe more dominant at the moment, which is based on empirical risk minimization. So you have some data. We have assumed the data was independent and with the same distribution. So the empirical mean will converge to the expectation. So maybe if you minimize this, you're going to be able to access to a minimizer of the expectation. And this is essentially what people are using at the moment. Okay, so this can be another game, is how you parameterize that function f. It can be a linear model, can be or a neural network. And of course, you need some capacity control, because if you minimize over all potential functions, very classical, you're going to overfit a lot, do very well in training data, but potentially not do so well on the testing data. So what has been changing in the recent years is that we went from classically like doing some capacity control based on constraining the set of predictors, like small norm, small number of parameters, to in fact doing some form of algorithmic regularization, where you stop your optimizer before you reach convergence, or you do like stop AGD before convergence. So I will not talk about it today so much, but I mention it because to me this is one of the key differences with when I started to do machine learning. All right, so now to do training, you have to do optimization. So the good benefit is that this gives me a job because I like optimization, and but the caveat is that it can be slow. Okay, so I guess many of you have already complained that an optimizer is too slow, and if you have not used big enough data. It can be slow, and what has been troubling me for the last 10 years is that it may not converge to the global optimum. Okay, so essentially, if you have a linear model and you use classical assumptions, you're going to have a convex problem. So things can be slow, but you end up, if you wait long enough, you end up converging to the global optimum. And this may not be the case if you have like neural networks. And I'll come back to that, of course, in the talk. So now I've set up the problem, and the goal is to work in high dimensions. Okay, so here I'm going to assume that I work with X being RD, and D can be like images, so like thousands or millions, or patches, a bit smaller, but still quite big. And what is classically referred to as a curse of dimensionality is the fact that if you want to make very few assumptions on your problem, and here I consider Lipschitz continuity as being very weak, I just want the tiny amount of regularity, then there is some bad news, and I really advise to read the book by Bakov. Then you can show that if you want to do well on any potential function like this, if you assume X, like take a ball in RD, then to do well, the excess risk, so how much worse you're going to do compared to the best, to F star, which is the conditional expectation, is going to be converging never faster than this. Okay, so it's the power of n. So when n goes to infinity, you do better. So you are learning, which is good. But the power is 2 over d or 1 over d. And if you take even d being like 10 or 100, 1 over n to the power of 1 over 100 is very slow. Okay, so this is a classical curse of dimensionality, here seen in convergence rates, but this comes up like in many places. Okay, so in other words, if you want to achieve some error epsilon, you need an exponential number of observations. Okay, so this is the bad news. Okay, but like all bad news, there are ways to circumvent it. Okay, this is the goal of this talk, is what are the assumptions which you can use to avoid having something like that. Why is that? It has to be possible because routinely we use learning algorithm on high-dimensional data. So there has to be some assumptions, okay, that we are using, and I will focus mostly on 3. One is supports of inputs. The other will be smoothness and also latent variables. And the goal of the talk is to relate those and to see if the techniques I've described so far are able to benefit from those like properties. So let's start first. So support of input. So here what I mean is that if you are in a d-dimensional space, but you don't occupy the entire space. Okay, so either you occupy a smaller subspace, okay, of dimension r, or a manifold of dimension smaller than d. Okay, so here my data has super dimension 2, and here it has super dimension 1. And what you hope, of course, is that in the curve of dimensionality, you replace d by r. Okay, so this is the goal, and we will see that most techniques will end up being adaptive. Okay, so this is the easy adaptation. In particular, it's not, you want to replace d by r. Why is it not so difficult? It is not so difficult because you can estimate the support of the data. Okay? You see some data, and you can do PCA if you want to estimate the subspace, or any form of manifold learning, or you can do simply ignore it and let the algorithm automatically adapt to it. So this one is not so interesting, important but not so interesting. The other ones are smoothness. Okay, so this is, of course, very classical in statistics. If I want to estimate a non-smooth function, so here, I'm going to require more data than if I want to estimate a smooth function. Then we may debate on how we define smoothness. Okay, and could be, so here I'm going to define smoothness in a very simple way, and there are many others. You can look at various wavelet decompositions, but I'm simply going to say that I'm smooth if I have S derivatives which are bounded, let's say in L2 for simplicity. So here what you expect is that it should be easier for this one than for this one. And in fact it is, and what you can show that the best you can do, and this will be achieved by min algorithm, is to replace D by D over S. Okay, so this is like a series of work and good books by Gyorfi and colleagues and Sibakov. So in the race, you replace D by D over S. So if you're very smooth, okay, if S, the order of smoothness is of order D, then you can start to have a power of n, which is not so bad. Okay, so now this means that if algorithms can handle that smoothness, we can deal with problems where D is large, but you need the function to be quite smooth. Then the last one, which I think is most interesting, is dependence on some latent variables. So you start from D variables, okay? So your D inputs may occupy the whole space, okay? So there's really no manifold of any kind or no linear subspace, but Y depends on X only through some simple function. So here I took a linear function. So this is on the left a function in two variables that depends on x1 and x2 quite arbitrarily. On the right, it only depends on that direction. Okay, so essentially, y is a function of a one-dimensional projection. And the hope is that if this dependence is only through a linear subspace, then you don't pay the d in the curse of dimensionality, but you pay just the r being the dimension of the subspace. Okay, so this is the hope, and this can be shown for that the best you can do is of that kind, and this also, of course, relates to the concept of sparsity, because what is a sparse model is simply exactly this, where my linear subspace is simply like the first of r variables out of D. Okay, so all the work on sparsity is essentially a subcase of this one, but by allowing let's say linear latent variables, okay, I'm going a bit further. Okay, so this is the like sparsity plus, but the goal here is to be adaptive to it. So what do I mean by adaptivity? So this is the goal is to be adaptive to some unknown property which I know exists, but I cannot characterize it fully. So what I want is that give me a problem, and if it happens to be easy, I want my method to be fast. And if the problem is hard, then tough luck, there's not much you can do, but at least you want to be adaptive to it. Okay, so of course, there will be some hyperparameter, and in statistics, it's a very classical problem, and I think we have experts in the room. And so here, I'm going to focus on the simplest form of adaptivity, so not the full one, but just adaptivity up to one hyperparameter. Okay, so for example, if you do k nearest neighbors, okay, I'm going to assume you can find k in a reasonable way, like traditional way by cross-validation. Okay, and the idea is that you're going to be adaptive is that with a good value of k, you can benefit from the various assumptions. Okay, so if you do like linear models, there will be like some penalty, L2 and L1. So if I give you the correct penalty parameter, then you can adapt. Okay, so same thing for neural network later. Okay, there will be a price of adaptivity, hopefully logarithmic in the number of samples, but I'm not going to talk so much about it. So now let's look, okay, let's look at the various techniques which I've shown. Local averaging, k nearest neighbor. So like linear models, like linear models in the parameters, like predictors based on Hilbert spaces, like smoothing splines or kernel methods, and neural networks. So the goal of the talk is just to highlight a fact which is start to be well admitted, that KNN is worse than kernels and worse than neural nets. Okay, and so what I want to emphasize is that this can be shown for clearly if you can optimize. okay? And the goal of the talk and the conclusion will be that if you know how to optimize, then indeed you have the superiority of neural nets, but can you really optimize? That's a different question. All right, so let's look at local overaging. So it's known that from quite a while, and probably earlier, that you'd get adaptivity to supports of the inputs. Okay, so no need to tell the algorithm if you're going to be in a small subspace. No need to do PCA, just like run it, and you're fine. However, it's not adaptive to smoothness. Okay, so and often people look at k-nearest neighbors as a method which is not adaptive and will be hurt by the curse of dimensionality. And this is true that you won't adapt to smoothness. So you may get a tiny bit in the convergence rates, but essentially you pay the curse of dimensionality in the classical way. In dimension D, if you want like neighbors around you, you need to have a lot of data to have neighbors which are sufficiently close to avoid any form of bias. So kernel, not very well. So now let's look at neural nets. And what I'm going to use as from now on is the same architecture for both kernel methods and for neural net, which is classical now. So I have a function f, which is a sum of nonlinearity. So this is a ReLU, a positive part. Then I have a linear part, bj transpose x. Then I have m of those bj's, and then I combine them linearly with some parameters aj. So this is a classical, like one-hidden layer neural net. And what has been also quite changing the last few years is that now m goes to infinity. Okay, so when I took the MVA, the masters here, we will never dare having m being too large. First, because our computers were quite small, and because we would believe it wouldn't work. But now, in the recent years, people take m quite large. All right, so what is the algorithm to solve that? I've mentioned empirical risk minimization. Okay, so this here I'm going to form the empirical risk. So here I put least squares for simplicity. I'm going to add some penalty, L2 penalty. And the algorithm is very simple. You just initialize all the weights randomly, and this is quite important. And then you do any form of LGD, of gradient descent, sometimes with stochastic versions. So now I'm going to look at two regimes which are traditional. The first one where I only optimize over the output weights, A. Okay, so I keep the B's intact, so just like sample randomly and never optimized again. Whereas if I optimize both, I'm going to optimize over both A and B. Okay, so now it's known from, I think, works by Radford Neal and Benrecht and colleagues, that in the first option, where I fix the weights, I'm essentially using random features. And when I have that number of random features go to infinity, I end up with a kernel method. Okay, so this is, I won't talk so much about it, but this is a method which I call a linear model. Why? Because since B is fixed, I only optimize over A, hence optimization will be convex and will be quote unquote easy. Whereas if I optimize over both A and B, then I have some nonlinearity in B, and it won't be convex anymore, and the optimization will be hard. Well, so what about the adaptivity of those two types of technique? So can I simply sample B's and never optimize over them? If I do that, then I'm going to be adaptive to the support. Okay, so this is not so much to ask. I'm going to be adaptive to smoothness. So this is something which is already interesting, and this can be seen. Okay, so on those two problems. So of course this works beyond 1D, but it's easier to plot in 1D. So if I'm allowed to vary the lambda, so the regularization parameter, I can go from underfitting to overfitting. So here I'm going to vary lambda, so from large to small. You see that up here you start to get a reasonably good prediction here, but here it starts to degrade a bit on the two sides. You can go from underfitting to overfitting, and depending on the problem, you may need a different lambda. So typically a smaller lambda on the right. Okay, and then you plot your nice convergence rate on the right. Okay, so if I get more data, okay, in the log-log plot, for the smooth target, the slope is steeper. Okay, so it's just like a simple simulation to show that if you're smoother, then you go faster. Okay, so this is all nice. But what about adaptivity to linear subspace, okay, to linear latent variable? Unfortunately, this is not adaptive. Okay, so in the simplest possible case, if your function f star depends on a single projection, even on a single variable, then you won't adapt to it, and essentially you won't benefit from it, and you're going to pay the curse of dimensionality if G is non-smooth. Of course, if G is super smooth, you may benefit from smoothness, but you would like to benefit from having G not too smooth and just being dependent on a linear projection. So let's go to neural nets for the last 5 minutes. So as I've mentioned, it does optimize over both A and B. And this poses like many questions, which some of them are open, some of them I won't talk about. Let me just describe them. What is the limit when m goes to infinity? So in fact, this has been answered quite a while ago. Okay, it's known that if you optimize over the 2 layers, you essentially have some an L1 norm hiding behind the scenes. Okay, something called the variation norm. This was highlighted quite a while ago. Second question, is it adaptive? Okay, and if I say L1 norm, you may start to believe that it's going to be adaptive. I'm going to talk about it. 3, how big m needs to be? This we don't know. It's one of the classical open problems in the area. We know that we can achieve good things when m goes to infinity, but we cannot really tell how big m needs to be. And final point, can you really optimize? Okay, and this will be the concluding aspect of the talk. So first look at the adaptivity. So first you should expect that we recover the adaptivity from the simpler techniques, okay, and we do. It's adaptive to support, adaptive to smoothness, all very nice. But now you can benefit from the L1 norm aspect. So the L1 norm is known to like estimate the good under some conditions the good like variables if you have linear regression. Okay, and you can here it's an extension of that fact to nonlinear regression because the G is a nonlinear function. And essentially, and this has been like looked at by several authors, you can get replace D by R in the rates. Okay, so you don't have the curse of dimensionality if you're able to estimate the W's. And the key here is that when you learn the B's, so the input weights, you end up learning the W's. Okay, so this is what is often called representation learning. You learn the good direction which are important for your data and not a random subset if you don't optimize about them. All right, so very simple simulation, just to highlight the fact that this can be seen even in very simple problem. If I just take a 2D problem here, classification problem, and this is like a figure made by Lenaik Shiza, and I add noisy dimensions. So here the problem is easy if I identify the 2 variables. Okay, it may not be easy if I add random noise. And if you take a classical kernel method where you optimize over only the output layer, the test error will go down. You end up optimizing, you end up like predicting correctly, but it takes quite a while, whereas the optimizing over the 2 layers works much quicker. Okay, so this is a very also toy experiment to highlight the fact that those effects can be seen very quickly. So for the last 2 minutes, let's talk about optimization. Okay, because those results were conditioned on the fact that I can optimize the neural net. Essentially, I can minimize this. Of course, I can minimize this one. Oops. Okay, so if I can minimize this, then neural nets are great. Question is it possible to minimize that? And this is where the what has been a key aspect in the last like 10 years in this area is, okay, is it the end of the talk or no? No. The punchline. Okay, so what has been the key aspect in the last like 10 years is that this is overparameterization. Okay, so when I took classes, I was told that don't take M too big or you're going to overfit. Okay, I was told that, and I think this remains true. Okay, But here, the new thing that if you take m being, it's going to be easier to optimize. Okay, and this is like a work which I've done with Lene Shiza, where we formally prove that if m is infinite, okay, then although you have a non-convex problem, you're going to converge into a global minimum of the cost function. Okay, so this is a benefit of other parametrization, but there is a coefficient property that, in fact, doesn't work. Okay, in the sense that if you want to overfit your data, it's not possible. Okay, let's have a look. Okay, so let's take like a 1D example. Okay, so here, this is my 1D example. I take 32 neurons, and this is very nice. I optimize, and I get like the nice piecewise affine function. Everybody's happy. This is the proof that if m is big enough, the proof. The empirical evidence that if, it's not the proof. Okay. And this is empirical evidence that if m is large enough, things optimize correctly. But then let's take like a bit weirder function like this one. Okay, so this one can be realized by maybe maybe eight ReLUs with m equals 8. I have enough power in my network to fit this perfectly. But with m being 32, I underfit. If I take m being 1000, I still like underfit a lot, and I think we try up to 10,000. You can't even fit that function. Okay, so this means that there is a strong underfitting. So this may be considered as a feature. We never overfit, but at least the way I was raised, underfitting is worse than overfitting, because underfitting, it can be like, it means that you can do like some trivial things. Okay, so here there is some strong underfitting. It's often called the simplicity bias, and this is totally not understood. Okay, what I'm aware of. I'm not aware of any word that will explain why things don't fit properly. Then you can, if you really want to do overfitting, okay, then this you can do it. And the simple way is to have two different learning weights. So if you optimize more aggressively on the output weight, then you're going to overfit. And if you make the difference in the learning rates very strong, then you can overfit. And here I was happy. Okay, I was able to overfit to fit perfectly. And if I had some noise, I can overfit to the noise. Okay. So here, I'm mentioning this because to me this is one of the key open problems, that it doesn't fit, but it not necessarily doesn't mean it's a good thing. Wow. So to conclude, I've tried to highlight the fact that a method is going to work well in practice if you're adaptive to potentially unknown properties about your problem. Okay, small support, smoothness, or latent variables. And if you ignore optimization, you should do really neural nets because it's adaptive to many more things. But the key issue is that optimization is difficult. Okay, so there is no, we don't exactly know neither in number of neurons or in time the way it totally behaves, even if it's super simple setup. You have some implicit bias, so I'm all for implicit bias, but if the bias is too strong and not controlled, I think that's a problem. And we go back to the classical notion of underfitting. And on this note, I will thank you for your attention and wish a happy birthday to Stefan.
Okay, so you spoke about like stochastic gradient descent, but for very modern architecture, people seems to use other optimizer like Adam, for instance, and seems to be important. So do you think there is an opportunity for mathematical analysis or something interesting behind?
Sure. So I think so here, if you start to use Adam, essentially you're doing some reconditioning of your problem. So you're going to navigate faster the profile, but I don't think it's going to escape, it's going to find a better solution, or it's going to avoid those like simplicity biases. Clearly, reconditioning is not a new idea. You should always be careful with conditioning, and it's going to be faster for sure, but I don't think it's going to evade the problem of simplicity bias.
Can I have time for just one quick question? So you mentioned this latent variable model as something that maybe neural networks, at least already in the shallow case, they are able to, in a sense, learn very well. So do you know, for them, in that sense, if now I replace these linear latent variables by complicated nonlinear latent variables, still have like a small dimensional of them, do you think that this could be a good mental model for depth?
I think. So first, I forgot one line, which is like, of course, here. I understand that this is like not reflective of the power of deep learning. Okay, so I'm naive, but not that naive. Okay, and that of course you want to go deeper. And I do think that's a way to see it, because you can have if you take like a three layer neural net, like 2 hidden layers. So for me, it's already super deep. Okay, and if you just select the randomly the first layer, then you're doing like it's like learning a smooth function. And on the smooth function, you do one hidden layer. You can do non-smooth over smooth. And this is a way, to me, to understand it a bit. You can learn in the first layers, randomness will get you the smooth features. And then you need to optimize to get the non-smooth features. But doing like the full optimization, which works better, of course, nobody knows exactly how it works, but that's open questions, okay?
Perfect.